Hi there, this is Richard Walker from Lucidate. Welcome to the second and final video in our series on EDA, Exploratory Data Analysis. In the first video, we started building a data pipeline to analyze and clean a lone default dataset. In this video, we'll briefly continue with that pipeline before turning our attention to a customer churn dataset to explore some alternative concepts. In the last video, we examined numeric data, in particular, how to deal with outliers. In this video, we're going to explore categorical data. Categorical data, typically encoded as text values, needs to be converted into a numeric form before it can be input into our AI models. Categorical data can be nominal, with features and attributes that have no order or rank. Think of country codes. Or it can be ordinal, where the rank of the data matters. Think of a credit score. It would be a mistake to convert nominal data into an ordered series of integers. For instance, if we took a set of country codes and gave each one its own integer score, our machine learning algorithms will assume that the order of the relationship is significant. Our algorithms will interpret numbers as either superior or inferior to one another, or, in this case, that the average of Scotland and Wales is Northern Ireland. This is clearly not what we want. To get around this, we use one-hot encoding. Here there's no order or ranking express between our features. We create dummy variables and assert that a variable is of a particular type with a binary 0 or 1 flag. For instance, if we have the category marital status and the range of values is married, single and divorced, we can use the encoding shown on the screen. A 1 in the first column means married, 1 in the second means single, and 1 in the third means divorced. This keeps the features unique, but implies no rank, no order. However, this comes with a cost. Firstly, we've increased the dimensionality of our dataset. One-hot encoding will add a new column per unique code value. A much more insidious problem is multicollinearity, which is frankly easier to animate than it is to say. Multicollinearity occurs when two or more independent variables are correlated to one another. Here we have accidentally introduced a correlation. As an example, look at the divorced encoding. If the first two values are both 0, then the third value must be 1. We can address both these issues by dropping one of our one-hot encoding columns. It doesn't matter which one. You'll sometimes hear this referred to as the dummy variable trap. For our ordinal variables, where there is an explicit rank, we can convert our codes to an appropriate set of ordered integers. So let's return to the pipeline we've built. Before any data cleansing, we can see that we had 1,491 missing home ownership codes. After we applied the IQR method outlier removal in the last video, this number reduced to 1,431. How might we deal with these 1,400 missing values? Are there some fields that might allow us to confidently impute some values for home ownership? Our scatter plot widget allows us to find informative projections. This suggests that it might be worth looking at annual income to impute some of the missing home ownership values. If we look at the distribution of annual income and split by ownership, there is some evidence that there's a link between income and ownership type. Higher income is associated with a mortgage, lower income with renting. Perhaps not a great surprise. Outright ownership does not seem to be influenced by annual income, which is perhaps a little unexpected. There isn't really a strong enough link between these variables to reliably impute the missing home ownership terms from annual income. In this case, we'll choose to replace missing home ownership values by the modal score, which turns out to be mortgage. we can compare the affected rows pre and post this block. Post substitution, we can see that our home ownership data is complete. Missing values here have been defaulted to mortgage. If we look at the data prior to substitution, we can see missing values in our home ownership feature. So we've made good progress with this pipeline. There are a few things to do. A key one is to transform our categorical values into one-hot vectors or ordinal integers. To do that, we'll first switch to our other dataset, which relates to customer churn. So let's open a blank canvas and drag in the dataset. We can see here that we have more features but less rows. We have some categorical data and a mix of ordinal and nominal features. As before, we can use our feature statistics widget to get a sense of the distributions of each of our features. To start with, let's look at our ordinal variables. These are education level, card type, and income category. We can use the Edit Domain widget to examine these features further and get the codes in the correct rank order. We'll first start with the education level. Once that is in order, we can then move to the card color category. Then once we've sorted that out, we can finish with the income classifications. Note, these values haven't yet been converted from their text values to numeric, as we can see with this data table view. We'll do the conversion later. At this stage, we've simply asserted the rank order of these ordinal values. Now, let's move on to the nominal values. We'll separate these values into their own branch in our pipeline using the columns widget. We'll name this fork in the pipeline nominal. Here we can separate the attrition flag, which is our target variable, the gender and the marital status codes. Then we perform the one-hot encoding with the continuize widget. This widget has a few options. If we look in the first categorical features column, we can see the one attribute per value is the choice that we want for one-hot encoding. We can select that value and then observe the results of the encoding in a data table. This is exactly as we expect, but currently not exactly what we want. We've introduced multi-collinearity. We've fallen into the dummy variable trap, but thankfully this is very easy to rectify. We can use an additional column widget to take out one column per feature. A final view with a data table shows us the correct one-hot encoding for our nominal values. No multi-collinearity, no dummy variable trap. So to finish, we just need to do a couple of things. Having ranked our ordinal variables, we now need to convert them into numerical codes so that we can input them into our machine learning models. We then need to merge the two branches of our data pipeline back together. One branch contains our one-hot encoded values from earlier, and the main branch contains the rest. We'll call the branch that contains the rest of the values main. We'll once again use the continuize widget. In our categorical data column, you can see that the option we want is treat as ordinal. Let's select this. When we hook up a data table, we can see that we've indeed changed all the text values to numeric codes. These codes are based on the rank order that we specified for these variables earlier in the pipeline. All that remains then is to hook up a merge widget to bring the two branches back together. We can verify that this merge is executed successfully by again using the very useful data table widget. And finally, we can save our cleaned up data. This concludes our short series on EDA. We've covered a lot of ground and the key topics in EDA. We've analysed and cleaned our data so that it can be fed into our models, improving outcomes. We've looked at strategies for dealing with missing data, outliers, and transferring character-based codes into numeric data. For missing data, we've seen that in a worst case, we can simply delete it. Alternatively, a better approach might be modal substitution, or replacement with a value strongly correlated to another variable. As you might expect, more sophisticated methods exist using AI techniques to impute missing information. They go by the names of k-nearest neighbours, or MICE, which stands for multiple imputation by chained equation. We've not covered them here, but we will address both in future videos. For outliers, we've looked at the IQR method. Application of this method massively improves generalization. In order to generate numeric data from coded text values, we've looked at rank order for ordinal data and one-hot encoding for nominal. With one-hot encoding, we have to be aware of the dummy variable trap. We've seen how to deal with this by deleting one column per feature. This is Richard Walker from Lucidate. Thanks for watching. Our next series of videos will be based around applying different AI and machine learning models to both the churn and loan approval datasets that we've analysed and cleaned in this series. Look out for that series of videos where, among other techniques, we will cover support vector machines, decision trees, k-nearest neighbours, logistic regression, and neural networks.